What if the world's next energy breakthrough is not rare, not lithium, not cobalt, not some exotic metal, but sand, ordinary sand? In Finland, where winter can fall to -30, a town is being protected by 100 tons of it, not inside a beach, not inside a desert, inside a giant thermal battery in Kankaanpää. And that is where the whole energy story changes. The modern world is chasing expensive batteries. It digs deeper, it refines harder, it fights for rare materials. But two Finnish engineers, Tommi Aronen and Markku Ilonen, asked a different question. What if the answer was already under our feet? Their solution does not look futuristic. It does not shine like a laboratory miracle. It is a huge steel chamber filled with fine sand. Then surplus wind and solar electricity attacks that sand with heat. The temperature rises to 500 degrees Celsius. The grains absorb it. The mass traps it. And instead of vanishing in hours, that heat can stay locked away for months. Think about that. Outside, the Arctic winter is closing in. Homes need warmth. The grid needs stability. Energy demand starts climbing like an alarm. But inside this silent container, a cheap material is holding the line. This is not a normal battery. It is not trying to store electricity forever. It is storing the thing people actually need in winter, heat. So the real question becomes much bigger. How does something so simple beat a problem so massive? How can sand, one of the cheapest materials on Earth, become a thermal fortress? And why would a low-tech pile of grains matter in a high-tech energy crisis? To understand that, we have to step into the cold. Because in Finland, winter is not just weather. It is the real test of the machine. Kankaanpää sits in a strange kind of pressure. The pressure does not arrive like an explosion. It arrives as silence. A long frozen silence. The air gets sharp, the ground hardens. Houses start demanding heat every hour, not sometimes. Not when conditions are convenient, constantly. This is where energy stops being abstract. It is not a graph anymore. It is not a policy debate. It becomes walls, pipes, windows, and people. A house either stays warm or it does not. That is the brutal simplicity of winter. And in a place like Finland, that simplicity controls everything. During parts of the year, wind and solar can produce excess power. The grid receives more electricity than it needs. For a brief moment, the machine has surplus, but energy is only useful if time cooperates. And time almost never cooperates. The wind may blow hard before peak demand. The sun may help before the deepest cold. The electricity arrives early. The need arrives later. That mismatch is the hidden enemy. It is not dramatic. It does not make noise. But it quietly breaks the system. Because if energy cannot be stored, it escapes. It passes through the grid like mist reinforcement. The supply arrives, then disappears. Then winter tightens its grip. Demand climbs. Heat becomes urgent. And the system has no thermal reserve waiting. That is the trap. Not a lack of energy alone. A lack of energy at the right moment. So the question gets sharper. How do you hold summer's surplus for winter's demand? How do you trap heat before the cold arrives? And how do you do it cheaply enough to matter? This is where most solutions get complicated. They move toward advanced chemistry. They move toward rare materials. They move toward larger, heavier, costlier battery systems. Each one tries to store electricity itself. But Tommi Aronen and Markku Ilonen looked at the problem differently. They did not start with a battery cell. They started with the final need. In winter, the town does not only need electrons, it needs warmth. So why force energy through a complicated chain? Why store electricity, then convert it later? Why not store heat directly? That small question changes the entire battlefield. Suddenly, sand is no longer just sand. It becomes a storage medium. It becomes a defensive wall against timing. It becomes a way to hold surplus energy hostage. The design is almost absurdly simple. Take excess wind and solar electricity, send it into a heating system. Push that heat into a giant mass of sand. Keep driving the temperature upward, 500 degrees Celsius, hot enough to transform the whole chamber. Not into something flashy, not into something delicate, into a silent thermal reserve. The grains do not need to move. They do not need a screen. They do not need rare metals. They simply absorb heat, grain after grain. Layer after layer, the whole mass begins to charge. And this is the part that feels strange. A high-tech energy problem meets a low-tech material. No glowing lithium cell, no futuristic casing, no exotic mineral supply chain, just fine sand inside a massive container. But yet, inside that container, something powerful is happening. Electricity that might have been wasted becomes heat. Heat that might have vanished becomes stored capacity. Stored capacity becomes a shield against winter. It is a reversal of expectations. The expensive solution is not always the smart solution. The complex path is not always the direct path. Sometimes the system fails because it stores the wrong thing, and sometimes it survives by storing the obvious thing. In Kankaanpää, winter keeps pressing from outside. It pulls heat from buildings. It stresses the grid. turns ordinary demand into a survival requirement. But inside the sand battery, the situation is reversed. The cold cannot rush in freely. The stored heat cannot escape instantly. The sand sits there like a quiet fortress. No drama, no moving parts at the center. Just mass, temperature, and time. That is what makes the image so powerful. Outside, minus 30 degrees is attacking everything. Inside, 500 degrees is waiting in silence. The town needs heat later. The sand is charged now. The two timelines are being forced to meet. This is not just storage, it is scheduling energy against winter. It is taking power from one moment, then defending it until another moment needs it. And that creates the next layer of mystery. Because holding heat sounds easy, but it is not. Heat always wants to escape. It moves through walls. It leaks through weak spots. It spreads into colder material. It searches for every failure path available. So why does this system not simply cool down? Why does the sand not surrender its heat immediately? Why push it all the way to 500 degrees? What is happening between millions of tiny grains? And how can that hidden heat return later? Not as a scientific curiosity, not as a lab demonstration, but as useful warmth for real homes. That is the real mechanism we have to break open. Because the genius of the sand battery is not magic. It is not that sand is special in a mysterious way. It is that the whole system uses sand correctly. It uses its mass, it uses its tolerance for heat, it uses its simplicity, and most importantly, it uses the fact that winter needs heat. Not tomorrow's perfect battery headline, not another rare material race, heat. So now the strange object in Kankaanpää becomes clearer. It is not a pile of sand. It is a time machine for energy. It takes surplus power from the wrong moment, then stores it for the right one. But to understand why it works so well, we have to go smaller, much smaller, down into the grains themselves. Because the secret is not just the container, it is the microscopic maze inside the sand. At the microscopic level, the trick becomes much clearer. The sand battery is not trying to be magical. It is trying to be brutally direct. Most batteries store electricity through chemical reactions. They need carefully controlled materials. They need metals that are difficult to obtain. But the town does not need chemistry first. In the middle of winter, it needs heat. That is the twist. The system attacks the problem at its final form. It does not ask, how do we save electricity forever? It asks, what does winter actually demand? The answer is warmth. So the engineers cut through the complexity. They take surplus electricity from wind and solar. Then they convert it into heat immediately. That heat is pushed into the sand. The sand becomes the bunker. The electricity becomes the supply line. And the cold becomes the pressure outside. This is asymmetric engineering. The system does not fight the hardest battle. It chooses the simplest battlefield. Once the heat enters the sand, charging begins. The temperature climbs toward 500 degrees Celsius. Grain by grain, the material absorbs energy. Nothing about this looks dramatic from outside. There are no moving blades at the center. There are no glowing battery cells stacked in rows. There is just mass, but mass matters. A small handful of sand cools quickly. 100 tons of sand behaves very differently. It becomes a thermal fortress. Heat now has to fight its way out, and that fight takes time. This is where the grains become important. Sand is not one smooth block, it is a packed army of tiny particles. Each particle touches other particles around it. Each contact point becomes a narrow thermal bridge. Heat can move through those bridges, but it does not get a clean highway. It gets a maze, a dense, irregular, microscopic maze. Every grain holds a little heat. Every contact passes some of it along. The deeper the heat travels, the harder escape becomes. It must cross layer after layer. It must move through countless tiny boundaries. That is why the container matters too. The chamber is not just a bucket. It is a controlled shell around the thermal core. Its job is to keep the battlefield sealed. Heat wants to leak into colder surroundings. The system tries to slow that escape everywhere. The outside world is cold. The inside core is extremely hot. Between them is a defensive structure. Sand is the stored mass. The container is the wall. Insulation is the outer armor. This is not perfect isolation. Nothing holds heat forever, but it does not need forever. It needs long enough to matter, and that is the engineering goal. Hold energy across the mismatch in time. Store it when supply is available. Release it when demand becomes urgent. That is why 500 degrees matters. Higher temperature creates a larger thermal reserve. The same mass can carry more useful energy, but it also raises the stakes. More heat means stronger pressure to escape, so the design must control that pressure carefully. It charges the sand without making it fragile. It stores heat without demanding rare materials. It turns temperature into a strategic reserve. And now the strange idea becomes logical. The battery is not valuable because sand is rare. It is valuable because sand is common. It can handle high heat. It is cheap enough to scale. It does not depend on a delicate supply chain. It only needs to win this one. Long-duration heat storage for winter, and for that target, sand becomes dangerous to ignore. But storing heat is only half the mission. A fortress is useless if supplies never return. So the next move is extraction. When the town needs heat, the system reverses flow. The hot sand begins giving energy back. Air or another heat-carrying stream moves through the system. It collects heat from the sand mass. Then that heat can enter the heating network. The stored surplus becomes useful warmth. Energy from the wrong moment reaches the right moment. That is the entire move. No miracle, no hidden fuel, just timing, mass, and heat transfer. And this is why the idea feels so satisfying. The system does not try to impress the eye. It solves the actual bottleneck. Winter does not care how futuristic a battery looks. It only cares whether heat arrives on time. The sand battery answers that directly. It takes excess renewable electricity. It locks energy into a hot physical mass. Then it releases energy when homes need warmth. So the low-tech material becomes high-impact infrastructure. This is the reversal at the center. Lithium and cobalt are not defeated everywhere. That is not the point. For phones, cars, and electronics, chemistry still matters. But for heating a cold town, the question changes. The best storage medium may not be rare. It may not even look advanced. It may just be the material that fits the job. Fan wins here because it is simple. It wins because it is available. It wins because it tolerates heat. And it wins because the need is thermal. That is the clean engineering logic. Match the storage method to the final demand. Do not solve a heat problem through unnecessary complexity. Do not worship the most advanced material. Find the pressure point, then build around it. In Kankaanpää, that pressure point is winter heat. The town needs warmth when nature refuses to provide it. So the system stores warmth before the attack begins. It waits quietly while the cold moves in. Then it sends heat back through the network. And once you see that, the sand changes. It is no longer ordinary ground material. It is captured time. It is delayed summer. It is a thermal reserve waiting for winter. The future of energy is not always shiny. Sometimes it is dull, brown, and almost boring. Sometimes the breakthrough hides in plain sight. Sometimes the smartest machine is simple. Not because the problem is easy, but because the correct question was finally asked. What do we actually need to store? In Finland, the answer was not electricity. The answer was heat. And once that answer was clear, sand became enough. The secret was never sand alone. The secret was using it at the right moment, the right scale, and for the right energy. That is the lesson hidden inside this whole machine. The breakthrough is not that sand suddenly became futuristic. The breakthrough is that engineers asked the cleaner question. What does the town actually need when winter arrives? Not a headline, not a miracle material, not a perfect battery for every problem. It needs heat, reliable heat, cheap heat, heat that can wait. And Finland found that answer in plain sight. While the world looks toward rare metals, this system looks downward. It looks at the most ordinary material imaginable. Then it gives that material one precise mission. Hold warmth until the cold demands it. That is why this story feels different. It is not about making technology more complicated. It is about removing the unnecessary steps. Electricity becomes heat. Heat enters mass. Mass holds time. Then winter arrives and the stored time returns as warmth. Outside, minus 30 degrees still pushes against the town. The air still bites. The buildings still lose heat. The grid still feels the pressure. But inside the chamber, the sand remains quiet. It does not look heroic. It does not look advanced. It just keeps doing its job. 100 tons of ordinary grains become hidden infrastructure. Not flashy, not delicate, but deeply useful. That is the larger message. The future of energy will not have one shape. Sometimes it will be sleek, electric, and chemical. Sometimes it will be simple, heavy, and hot. The smartest solution depends on the real bottleneck. And in Kankaanpää, that bottleneck was winter heat. So the sand battery is more than a strange invention. It is a reminder about engineering itself. Start with the need. Find the pressure point. Then use the simplest tool that can survive the job. Because sometimes the material under your feet is enough. For more original engineering stories, stay with this channel. The next ordinary material may be hiding another solution.